Our first presentation this afternoon is Systems Administration, Server and Process Behaviour by Mark Smith. Mark Smith has done a little bit of everything, as most sysadmins. That means a little bit of DBA, a little bit of, obviously a bit of sysadmin, a little bit of software engineer, and he's even managed an operations team. One of the other aspects of his life, which I have to shake his hand for, he believes strongly in the Oxford comma. Thank you.
All hands.
And he wishes to move back to Iceland one day. So please give a warm welcome to Mark Smith.
Thank you all for coming. Is this thing on? Can you hear me in the back? All right. Welcome to the afternoon tutorial, Servers and Processes, Behavior and Analysis. I'll give you kind of an overview of the next, I put 90 minutes because I can't read a clock. It's actually 100 minutes, give or take. We'll go over a bit about what we're going to talk about, as you do at the beginning. I'm going to talk a bit about servers, trying to give you a bit of a mental model for thinking about them. We're going to get hands-on. This is a hands-on tutorial. I will hope that each of you has a laptop or you can look over the shoulder of somebody next to you and hope that the wireless cooperates. It has been tested, but I didn't, we've got 50 people in the room now, so we'll see how it goes. Fingers crossed. So far, wireless has been great at LCA, so kudos to the team that has done that. Then we're going to talk about processes as opposed to servers, kind of a different way of looking at things, and then we'll do a bit of wrapping it up. So I do have a bit of caveats, and if you get up and leave after this, that's fine. This is a tutorial aimed kind of at engineers who are interested in getting their feet wet with systems administration. Haven't really done a lot of it in the past, like maybe you've connected to a machine, you've used SSH, you know how to do that, that's fine, and we expect a bit of that, but we're going to gloss over a lot of the really advanced things, like we start talking about L1 cache, or things like that. Like if you have to worry about that, you're above the level of this talk. Questions are, feel free to ask. We do have a microphone somewhere, up here somewhere, magically. Oh, you've got it, right. So if you're going to ask a question, please either wait for the microphone or allow me to repeat it for the benefit of our recording audience. And the slides will be available online. There's some tips and tricks in here that are, I find, helpful and useful, and hopefully you will as well. So a bit about myself. I'm Mark Smith. There's my email address if you want to get a hold of me. I've co-founded Dreamwidth Studios, which you may or may not have heard of. It's an open source fork of the LiveJournal project, which is a blogging software started back in 1999. Dreamwidth is a vibrant open source development project. We have dozens of volunteers over the last 4 years and hundreds of patches a year, and pretty good group. My co-founder is Denise in the audience there, so hello. I've worked at Google, I've worked at Mozilla. I'm in the Silicon Valley, right? I've worked for startups, bigger companies, little companies, and done a bit of everything from, I spent a while as a MySQL DBA because I thought that might be interesting. And it was in very specific ways. As a operations sysadmin, working with Mozilla when they rolled out Firefox 3 was a pretty fantastic experience. Delivering software to 100 million people in 24 hours is pretty exciting. So, but I jump back and forth right now. I'm doing a little bit more of the engineering side of things at Bump Technologies while managing their operations stack. With that, we're going to get started. First, we're going to talk about servers. What is a server? It is a machine that takes input and makes output. This is just a computer, right? Your laptop and a server are not very different. You do things on them. They take inputs, keyboards, mice, whatever. They make output. Servers are the same. They take inputs, network connections, data from your disks if you're processing data, stuff like that. Weather patterns, whatever. At their core, that's all a computer is, and that's all a server is. They're not mystical black boxes. They sit in a data center, you don't really see them, but they're not more complicated than the machine you're using right now. You've gone shopping for computers, I'm sure. i7, i5, Xeons, gigahertz, bytes, all that sort of thing. I'm going to assume you know what those are. But that's all a computer is. It's a sum of components that make up the whole. But we're going to go into each of these components, and we're going to talk a bit about how we measure them, how we actually know what they can do, and how we know if they're doing what they're supposed to be doing, how we know if they're doing their job well. And sort of my opinion on systems administration, I mean, as with most things in technologies, you ask 100 people, you get 100 opinions. I think systems administration is just the care and feeding of all these different components and understanding how they work, right? So this is my list of how I measure components, and we'll talk about these for each of the different things. Capacity, latency, throughput, what happens when it's full, what happens when it's thrashing or it's in high contention. You measure pretty much anything like this. If you want to talk about cars, you can measure the capacity of the engine and the horsepower, the latency with the torque, the throughput with its top speed or its quarter speed. You know, whatever you want to talk about, you can measure vacuums with the same sort of thing. These are just sort of the three metrics that you measure pretty much anything. How much can it hold? How quick is it? How much can it push in and out? Full state, we'll talk about for each of the components. What happens when it's full? Different components of a system behave differently when they're full, and as a sysadmin, you need to know kind of how to react to that. Thrashing state, also very important, especially nowadays, and we'll get into that a bit more. What happens when a lot of people are trying to use the CPU? What happens when a lot of people are using the disk, or a lot of software, or a lot of whatever you have? And what can you do as a sysadmin to diagnose that, and what are your options? We'll talk about RAM first. This is all pretty basic. It's measured in bytes. You have a machine that probably has a couple gigabytes of RAM. Servers these days, you know, you might deal with one that has 8, 16. Half of the ones I deal with have 96. We have a couple that have like 128, or they go up to, you know, hundreds and hundreds of gigabytes of RAM these days. It won't be long before we have terabytes. Latency, nanoseconds. So RAM latency is how long it takes to say, I want this bit of data at this location in RAM. How long does that take to happen? I mentioned this, and we'll mention this for each of the components, because eventually you'll have to make trade-offs. You'll have to understand what happens when data is moving from RAM to disk, for example. What are the different performance profiles you can expect? It's usually measured in bytes per second, although you really don't usually worry about that, because it's gigabytes per second these days. For the most part, you don't really deal with systems that are pushing that unless you're dealing with like high-performance computing, and in that case, you're probably not going to learn a lot from this talk, and you can teach me something. So. RAM is a kind of a binary full. It's full or it's not. And when it's full, that's it. It's just full. It doesn't really thrash. It's random access memory, so you can randomly access it all you want. It's designed for that. Rotational disks, these are spinning disks that we're all pretty familiar with. You've probably gone shopping for these in the past and optimized for seek time. Is it 6 milliseconds or 8 milliseconds? And you know, the faster seek time is going to make you boot up faster, and that's awesome. But it really can impact servers. Latencies in milliseconds. We'll talk a bit about, I put in a bit here a little bit later in the talk for people like me who come from the US and don't grow up with the metric system and, you know, nano, milli, pico, whatever, what is all that stuff. But latency on a disk is measured in milliseconds. Throughput is also bytes per second, although it's usually on the order of 100 megabytes per second for streaming reads and a lot less for random reads or writes. Full state is also binary. When a disk is full, a disk is full. Thrash state, however, on a rotational disk, it's really bad. You've probably noticed this if you tried to launch multiple programs at the same time. You launch Photoshop, you launch you know, Firefox, you do all this thing, or Firefox launches and it loads 18 tabs, and your machine starts, you hear the disk grinding for a bit because it's jumping around trying to load everything from cache. Performance really drops off when you start talking about the thrashing for a disk. These days, though, we talk a lot about SSDs because we're really moving in that direction as far as servers go. Capacity is same as disks, bytes. Latency is in milliseconds, but it's still about 100 times faster. We'll talk a bit more about that in a bit. Throughput still bytes per second. Full state is about the same. It's full or it's not. Thrash state, however, it's like random access memory. You can access any part of the disk with roughly the same speed because it's effectively RAM. It's just slower. CPU, you know gigahertz, nothing particularly fancy there. Throughput and latency we're not going to talk a lot about here because it gets really complicated, especially when you start getting into NUMA and you start worrying about, well, a quarter of the RAM is on core 1 and a quarter of the RAM is on core 2, and the speed to access RAM on a different core is actually slower than the speed to access RAM on your core. We're not really going to go into that here. Full and thrash state, same thing if you've launched a bunch of programs at the same time on your computer, you have felt everything slows down when you go to Alt-Tab or Command-Tab or whatever it is on a Mac. You notice it'll draw the window and then it'll draw what's inside. Your system takes a little bit to go while the CPU is being pegged. Networking, we don't really talk about capacity of a network. We do talk about latency. In a data center, your machines are pretty close together. So they're usually on the order of a millisecond or less apart, half a millisecond maybe, but it's still on that order. Throughput, just to confuse you, is in bits per second. You've probably heard of a gigabit network card, or back in the day, 100 base T, 10 base T. You don't really see those too much anymore, especially in data centers. Now it's pretty much all gigabit. We're moving in the direction of 10 gigabit, which would be nice because honestly, the biggest pain, in my opinion, is mostly gigabit still. The CPUs and RAM and disks are so fast these days, and the networks are just slow. So one day, we will be on 10 gigabit or beyond. We're not going to talk a lot about TCP, UDP, that sort of thing. Those are protocol-specific stuff, and that's something that I feel that engineers usually learn a lot more about. And since we're focusing on systems administration, we're not going to go into that a lot. But thrashing state for a network, it can drop packets, and the behavior of that depends on what your protocol is. All right, I said that we'd have a brief slide on this. Since many of you are probably from around here, you're probably familiar with these, but it helps me to think of the order is very different. When we were talking about RAM has an access time of nanoseconds versus disk has an access time of milliseconds. So one seek on a rotational disk, about 6 milliseconds. That's pretty fast to you and me. You can do dozens to 150 of those a second. That's pretty good. I can't count anything 150 times a second. SSDs, however, are about 100 microseconds, which is about 60 times faster than a rotational. So for every one seek you do on a rotational disk, you do 60 data accesses randomly on an SSD. The difference between SSD and rotational performance is huge, and that's a big reason the industry is moving in that direction for many servers. RAM, on the other hand, is a whole different ballgame. 1,600 times faster than an SSD, and these numbers are based on sort of averages. There are, like, if you talk about SLC versus MLC SSDs, the times change. We're not going to go a lot into that, but just as a rule of thumb, rotational disks are really, really slow. SSDs are pretty fast, and RAM is just way faster. So that gives us a little bit of framework. These are each of the components that make up a server. And in my opinion, the job of a systems administrator is to understand what each of these components does, how it works, and how it behaves. A lot like a mechanic on a car will understand that there's a problem based on just the sound of the engine without having to open it up. As a sysadmin, when you've spent enough time looking at servers, playing with them, and working with them, you get a sort of a feel to go, oh, actually there's something wrong here, even though you haven't actually seen what the problem is. You get an understanding of what is going on. So we're going to get a little bit of hands-on here and see how it works for the whole room. For those of you who are on Macs, you'll need your terminal. For those of you who are on Windows, you'll probably need something that is SSH, like PuTTY, or whatever your favorite terminal is. If you're on Linux, well, I'm sure you know how to open up an SSH terminal. I have a VM running on my Mac here that we're all going to share. This is the valid IP. Yeah. Please be nice. It would be nice, if we all learn something here. More than just like, oh, it breaks if somebody does something terrible. You're not root. You don't have full sudo. Yes. Bravo. So go ahead and open it up. If you have SSH, or if you have a terminal in Mac or Linux, you can use this command and it should just work. Port 2222, the user demo at this IP. If you're on Windows, you'll have to use PuTTY. And I don't have the screen in front of me. I should have took a screenshot of that. But you'll need to select SSH, change the port, and the IP address. Do we have any success yet?
I'm in.
A couple are in. You got root. All right.
A lot of people, there's like, we're up to PTS 40.
Nice. If you're having trouble, feel free to say something and we'll make sure you get in so you can, take part if you're. I'll give it a minute here. People are typing. So for the purpose of this demo, we're pretending that you are connected to a server in a data center. I've told you that you're connected to a VM on this laptop, so you kind of know what to expect. But we're going to pretend that You show up at work or whatever, your sysadmin has quit in a rage. He's like, you know what, I'm done with this. And somebody says, yeah, you know, here's our server login. It's your job now. And you're like, great, thanks. So, it's dark in here. The first thing that I kind of do when I'm handed a machine that I don't really understand is try to get a little bit of information about it. I just want to get a sort of understanding, like when I walk into a room, I do basic checks, like is the room on fire? No, okay, it's probably safe to stand in here. You know, is there smoke, can I breathe, etc. The stuff that you do in the background. You can do similar things when you start talking about connecting to a server. Each of these are commands, you may have heard of them before. Give them a shot. Go ahead and run the uptime command. Uptime is going to tell you how many users are connected, and actually how many are connected right now?
47.
47 users. That's seems like a quorum of the room, so excellent. The free command tells you how much memory is free. The df command tells you how much disk space is free. Of course, by virtue of telling you how much is free, they also tell you how much is in use and what the total is. So, what is the load average right now? Somebody, anybody? 0.54. That's pretty low. How about memory? How much memory does this machine have? There should be a column on the left that'll tell you, sorry? About a gigabyte, right? Pretty straightforward. What about disk space? 60 gigs? Yeah. So it's a little VM. If you're actually playing with servers in a data center, they're probably going to be way bigger. So, I mean, on the other hand, they might not be. If you're talking about a little EC2 instance, it could be pretty small, right? All of these things that we talk about work the same pretty much depending on the size of the machine that you're talking about. Generally though, if larger machines crash harder. So, and they take longer to bring back up. So let's talk about that first command, and let's talk about load average. Load average is sort of a boogeyman of a number. A lot of people say, oh, the load average is 97, that's terrible. I'm not actually asserting that, because we don't know. Low is good. I mean, low means the machine is not really doing a lot. It means the machine thinks that it is not really busy. There's not a lot of processes running right now. So rule of thumb, low is good. High could be bad. We will reiterate this a number of times through this talk, but basically, a lot of systems administration is having a feel for your machines and your software, knowing how they work and how they behave, knowing what their good states are and what their bad states are. Same as in, you know, jumping in a car. Your car may sound a certain way. You jump in someone else's car, you can't say their car is bad because the engine sounds different, right? It's a different engine. I like cars, I like planes, so I use a lot of those metaphors. Systems are very much the same. You will, if you have a bunch of systems, your web server will probably run really hot on CPU and maybe RAM, but it might not touch the disk. Your database, on the other hand, might run really hot on RAM, really hot on the disk, may not touch the CPU a lot. You get to know what the normal profile is of your machine and how it behaves. So we've talked about a few commands, and we'll come back to those. They'll help us a bit to diagnose when we get into some examples. So we're going to talk about top. You've probably heard about top. Top is sort of one of the first things people learn. What is going on with this machine? I run top. So everybody should go ahead and run top. You just type top on your current terminal. Someone's running DD. All right, all right.
What was the password?
Demo. Password is just demo. Demo what?
Demo, so it's using demo password demo.
Yeah. There. Yeah, come on, be nice to it, be nice to it. All right, you get in? Cool. All right. So, assuming that everybody's kind of got top up now. Yes? Great. Top allows you to see basically what is going on the machine. It sorts the processes by a number of things. You can actually do a lot with top. We're not going to talk about everything. We're going to talk about the really important things that you need to know probably all the time. So if you look at your screen with top, at the top of it, no pun intended, you will see the current state of the machine. This is data that you just were looking at. It'll show you how much RAM there is, how much RAM is free, what the CPU is doing. Interestingly, it breaks down the CPU by 4 values, and we'll come back to these, but you'll see user, system, idle, IO wait. In certain environments, you will see more hardware IRQ, software IRQ, and stolen time. We're not going to talk about those here. In top, if you press Shift P, capital P, the list should change, and if you look at the CPU column, you should see it sorted by CPU. There's probably not a lot going on unless somebody's doing something.
Somebody's being a jerk.
Somebody's, be nice. You what?
I'm watching it.
Okay. If you do Shift N, you can sort by memory usage. And you can see what is using memory on the machine, which is, somebody probably wrote a little Perl script and is sucking up memory. That's fine, we'll get there. But this is sort of a quick hit to show what is going on the machine, what is currently the largest offender in terms of CPU usage and memory usage. So, all right, now we'll have a demo, and I will have to alt tab a bit here. All right. Great. So I have done something on the machine, running a script. What I want each of you to do is start going through, like let's say you get an alarm or somebody tells you, hey, there's something going on this machine. So you want to kind of figure out what's going on. Users never report very good things. They just say it's kind of broken or it's kind of slow, and that doesn't really tell you much. So whenever you're investigating something, you always usually have to go in and see what's going on. So go ahead and try uptime. Take a look and see if the load average has changed much. It might have gone up a bit, but that's not really going to tell you a lot. If you check free, has the memory usage changed substantially? Is it very low free? Probably not. If you check the disk usage, it probably also looks fine, modulo the DD stuff somebody was doing. But go ahead and run top. And then sort by memory, sort by processor. Tell me if you see anything that is different or out of the ordinary. Yes, there's a script running, Perl script. How much CPU is it using? A lot. So from somebody reported, hey, this machine's acting kind of slow, something's going on, you've nailed it down to this little script called 1-CPU. It's pushing, well, it would probably go to 100% if there weren't 50 people on the VM, but 80% I'll consider good. But is this broken? Is this bad? No. Yeah, exactly, right? It's running, but there's nothing saying that that's bad, right? It could be normal for your system to run at 100%. I can't tell you that. That is, as a sysadmin, I mentioned earlier, I mentioned again, you have to know your environment. You have to learn what these machines do, what they feel like, how they behave, and what normal is, and that's a whole can of worms. So now we will go to another example here. Something else is happening, and this will take about 10 seconds to warm up. But go ahead and start cycling through your steps again. Check uptime, check free, check DF, check top. Tell me what you're seeing, tell me what you're experiencing. Low memory usage. So, seems like the machine is running out of memory? Is the what? True. We will get to the a little bit later. Does the machine feel sluggish, right? Lots of memory is being consumed. If you're looking at top, you'll see swap. You'll see some process called 2-memory is being a bad citizen and is consuming all the memory, and then some. So you've noticed it feels sluggish. Everything is just slow. This is sort of an environmental thing that you will come to know about your machines. Some machines feel fast, some machines feel slow. Typically databases always feel a little slow because they're always doing I/O, and the kernel, when it's really full of I/O, as in this condition, acts a little more sluggishly. So let's actually dig in a little bit deeper here. Let us see what's going on, what we're doing. VMstat is a useful tool, and one that I come back to a lot because it condenses a lot of information into one line, and it gives you updates every second. So if you queue out of top or Control-C to get out of top, go ahead and run vmstat-sm1, capital SM. You don't need the SM. I like it because it changes the display to use megabytes instead of the normal blocks or 512K byte or 512 bytes. Once you've got that running, you should be seeing lots of numbers on the screen. You'll see the column at the top. It's broken down into, on the right side, processor or CPU usage. There's a BI and BO section, an SI and SO section, and some other memory-related sections. You should see, what are the SI and SO columns doing? It's swapping. This is how you can prove that a machine is actively swapping. BI and BO, or blocks in, blocks out, those are I/O. This is talking about reading from disks and writing to disks. This is a good indicator that your machine is doing a lot of I/O. The CPU column on the right, again, we'll see that it's broken down into 4 sections. User CPU. User CPU is what you as a user is using, what you're doing, your process. System CPU we'll talk a bit more about later, but it's what the operating system is using, what the kernel is doing. Idle is idle, cycles that the CPU has nothing to do. And wait is, to simplify it, basically I/O wait, when a process could be running, but instead it is waiting for some data somewhere. So let's talk about swap. We talked about RAM. We know RAM is finite. You have 8 gigabytes of RAM, you can store 8 gigabytes of data, no more, period. You can't just add more at the end. You can go buy more RAM, sure, but you probably don't have that luxury if you're in the middle of a problem. Not all RAM is used equally though. If you're an engineer, you've probably dealt with caches. You've dealt with maybe an LRU cache, which is where you have some data that you use more frequently than others, and you take the data you use less frequently and evict it from the cache, you get rid of it. The kernel tries to do the same thing. It says, you know, I've got 8 gigabytes of RAM and I've got 100 gigabytes of disk. I've got way more disk than I do RAM, so RAM is at a premium for space. And the kernel keeps track, roughly, of how each segment of RAM is being used, each page. And it can decide that a certain page of RAM is probably not going to be used in the near future, and it'll swap it to disk to free it up, to free up the RAM for somebody else to use. That's great. It's wonderful, right? On a consumer machine, swap is fantastic. But remember the timing slide. When we were looking at disks, when we were looking at RAM speed, RAM is nanoseconds. It is very, very, very fast. A process that is running all in RAM can do a lot of data, a lot of calculations, etc. A process that is using disk for its data is going to be a lot slower. Even if it's an SSD, it's still, 1,600 times slower? So swap is mostly useful for consumer machines. It is, in my opinion, pretty much bad on servers, like always bad. If your machine is swapping, and I mean actively swapping, like currently writing blocks in and out, in and out, in and out, that's probably indicative of a problem on your server. There are very few situations that I've seen otherwise. But I say active swapping because the kernel sometimes tries to be helpful and swap things out even though your RAM is not full. If you get up to 70% or 60% and sometimes even way less, the kernel will say, this page hasn't been used in 5 minutes or whatever, I'm going to swap it out. Just so that if there's a RAM burst, I'm ready to go. If you look this up online and you say, my kernel is swapping data, I don't want it to be swapping, people might tell you to start tuning the swappiness of the kernel. This is a rabbit hole. It never ends well when you start trying to tell the kernel what is best, right? There are things in the kernel you can tune and are great to tune, but there are things that are not, and in my opinion, the swappiness value doesn't usually end well. But as a sysadmin, your mileage may vary, and you'll have your own opinions and war stories and battle scars. All right, we're going to move on to another example here. And I will, if I can get the machine to come back so I can kill my process.
Yeah, kill it for me.
Come on. A good object lesson of swapping. Sometimes you will not be able to get the machine to do what you want it to do. I see somebody has also found wall. Hi, hello. Come on. Is it what? Yeah, it's
not responding.
yeah. I'm not getting anything on the terminal either. I might have to.
Responding on Teams, but
Might have to. It's dead, Jib. She's giving it all she's got. Oh, my Perl script is like out of memory, out of memory. It's like, yeah.
it's memory.
Yeah, it's like that's sort of the design goal here. So let me see if I can get this to. Yeah, I might have to.
What about all that production stuff that's running on that?
Oh yeah, when a machine goes into full swap, it often dies. Right, there's often little you can do to bring it back. Well, yes! Are you still connected? I don't know how that's possible. I completely paused the VM and rejiggered it. All right.
Yeah, wow, loadout 82.
Heck yeah. Because everybody was trying to run something, yep. So if you run uptime, you'll see a good example of load average being pretty high, and probably meaning that there's probably something going on. Yeah, it'll come down. If you go ahead and run free again, take a look and you'll see things are a little better. A little. Yep. All right. So we're going to take a look now at another example here. I'm doing something else to the machine less catastrophic this time.
We hope.
We hope. No promises. Try uptime, free, DF, top. Take a look around. See if you can see anything. And then give this other command, this iostat-kx1. Give that a shot. You might have to widen your terminal a bit if it wraps around, because it's a very, very verbose command.
I think you forgot to install it.
Oh, no. What?
That's all right.
Okay. All right. I was like, I was just running it. This should be there. So this command, iostat, as you might imagine, is I/O statistics for your machine. It looks at each of the mounted devices and keeps track of what the requests are on those. As far as what the kernel sees, it keeps track of reads, writes, the average size of those, the average wait from the time a process issues a request for a read or a write, how long it takes roughly for the device to service that request. And then it has a magic utilization percentage. This is a magic number that is sort of a guess based on what the kernel thinks the performance of this device is. What is the utilization right now? Is what? 0. Is it? Shouldn't be 0. Oh, yeah, it was totally 0. Because it was prompting me for a sudo.
There we go.
Something's happening now. Wonderful.
128.
Yeah, so it's a percent, right? It should go to 100. 100 is full. Well, no. It's going to overshoot that. You'll see this a lot too sometimes in CPU usage. You'll see it at 98 or 103. It doesn't mean your CPU is suddenly going faster, although it could. It's just these are imperfect estimates by the kernel for performance. because it's more concerned about actually running your software than it is, are you actually hitting the limits of this disk or of this CPU? It tries its best, but it's sort of kind of hard to do. Also, try vmstat again. The vmstat-sm1 command, you should be able to hit up. You can exit out of iostat with Control-C, but if you hit up a few times, you should be able to recall your vmstat command. All right, it's running again. vmstat should start showing some data now. The BI, BO columns may be acting up a little bit. A little bit, all right. So, disk usage is high. IOStat told you that utilization was high, and vmstat has confirmed that there's a lot of I/O happening on this machine. It's reading and writing from disk a lot. But if you ran top, you probably saw a process called Bonnie at 20% CPU, something like that. So the CPU is not pegged. If you looked at RAM, the RAM is not pegged. It's not full. The machine's not swapping. The disks are kind of busy. Does that matter? I don't know. It's your machine. So as a sysadmin, it's kind of for you to know if this is a problem for your users, if this is a problem for the business, if this is something you have to worry about. So what does it mean? We were sort of just talking about. You've gathered a lot of data. You've kind of gotten a feel for what could be happening on the machine, how it could be behaving and responding. Is it healthy and happy? Yeah, I don't know. So solutions. We can talk about solutions to this, because it's kind of funny, but it's pretty easy. Right? If you're out of RAM, you can install more RAM, or you can optimize your software. If you're an engineer, you've probably dealt with time versus space trade-offs. Make your algorithm faster, takes more RAM. Make your algorithm a little slower, takes less RAM. Depending on the constraints of your environment, the budget of your CFO or whoever else handles the purse at your company, or yourself, depends on what solutions you're going to need to do. A lot of the times I find in systems administration, the solutions are pretty straightforward. U-limits. We will get to U-limits in a bit when we talk a bit more about processes. The question was about U-limits. A lot of problems are pretty straightforward to understand. Even U-limit ones, you're like, oh, I have a limit of X, I'm out. I only have 8 gigs of RAM, I'm out. So it's straightforward to understand. The solutions may not be so easy though. Business constraints, or what you can do, or maybe you can't even take the machine offline. Maybe you've got a situation where you don't want to take a downtime, and it's the middle of the day, and you have to make sure your system can limp along to get somewhere. So we're going to segue away from servers for now. We're going to start talking about software, the things that are actually running on machines. And we're going to get it more into, well, software that runs on a machine. Can I get kind of how many of you are engineers, programmers, write software for a living? Okay. How many of you are sysadmins? All right, so a lot of sysadmins. I hope you're going to get something interesting out of this, or at least having fun. So software is stuff that runs. You all run software, MySQL, Apache, et cetera, et cetera, et cetera. You've probably heard terms single-threaded, multi-threaded, compiled, interpreted, et cetera. All of these things influence how software works and what you can understand about it. Like, for example, single-threaded program can only use one core on a machine. Right? You can have a quad-core CPU with hyper-threaded, so you can effectively run 8 bits of software at the same time. But if your app is single-threaded, it uses 1/8 of your machine. That is a limit of the software. You can multi-thread it, which is a larger task, or buy a faster CPU, which is probably kind of overkill. Software has certain resources and inputs and makes outputs. It is a lot like servers, it's just software. There are more constraints though, more things to think about when you're talking about running software. He mentioned U-limits. Talk about open files and sockets, or file descriptors. Permissions, CPU limits, which we talked a bit about, single-threaded versus multi-threaded. there's a lot more to think about when you get into the software world. So I'm going to run the next demo. If I can convince this one to stop. All right. There's something else running now. Let's go through the usual suspects. So is the RAM full? Is the disk full? Is the CPU busy? Is anything amiss? Now, the system looks okay. It's not swapping. It's not using much memory. If you run top, you probably won't see anything unusual at the top of the process list or the top of the memory usage list. If you run vmstat, it's going to seem pretty bored. If you run iostat, utilization is going to be 0. Maybe a few things in and out. Nothing to worry about. So let's talk about file limits. We all know what files are, so I'm not really going to talk about that. But when a program wants to open a file, it has to talk to the kernel. It has to say, hey kernel, here's a file name. I want to open that. The kernel then returns what's called a file descriptor. It's a number. It'll say, all right, your handle is number 7. You've opened the file /etc/password. It's handle number 7. What happens though is that there's a limit to this, because Linux is designed as a multi-user system. You don't want to allow one user to completely take up all the resources of the system. So there are things called process limits. You're probably familiar with PS. I didn't cover that because I assume a general familiarity with PS. These are my favorite flags. You can use whatever makes you happy. But PS grep /files, and this is the program that is currently running. You should be able to get a PID, which is a process ID. This is the reference the kernel has to the process that says, I know what this program is. Like, it doesn't care that the program is called /files. It could be called anything. All it cares about is this is process number 13,422. I don't know what the PID is right now. So then try running this command, cat, which is to show the contents of a file, /proc/ the PID number that you just got, /limits. Is everybody finding that okay? All right. You should see about 12 lines of output that say a bunch of random things, max number of open files, total brain fade, memory usages or CPU limits. I forget exactly what's in limits. But the important one for this one is max number of open files. Does anyone have that number? 1024. Power of 2. It's computers. Powers of 2s are everywhere. They don't have to be a power of 2. It could be 13,000, whatever. In this case, the default for this user on this kernel is 1024. It varies by kernel, it varies by user, it varies by environment, it varies by software, it varies by if you're root or if you're not. The /proc/ the PID /limits is a good way to see what that is. You can also, on your terminal, type ulimit -a. So letter U, limit, space, -a, enter. And you'll see what your limits are right now. If you were to run a program, it would have those limits because those are your limits as the user. It probably says 1024 files, and a bunch of other things. You can change those limits, but we'll talk a bit more about that in a bit. So let's talk about, we suspect in this particular case that this program is having a problem with files. That maybe it's hitting its limit. How can we prove that? LSOF, like ls lists files in a directory, LSOF is list of files, but it's list of files that a process is using. With the arguments -np, the PID. N says don't resolve DNS, which will be important in a bit. P is, I'm going to give you a PID. You'll probably see a lot of output, right? Lots of lines of /tmp /xyz random numbers, or incrementing numbers. Has it hit the limit? You can try this. WC is a word count program. -L says count the number of lines in an input. Is anybody not familiar with piping and what is going on with the pipe? So I can go over that. All right, you're all basically familiar with shells and you've piped things to things. Great. So you're piping the output of LSOF here, which is one line per file, to WC-L, and it's probably giving you a number back that says like 1,030 something.
1036.
1036. Well, we know our U limit in this case is 1024. It's above 1024. Is that a problem? Well, it's only a problem if it's actually opening files, right? We don't know. If the thing actually only opens 1,024 files, then it could be happy, right? It could be not having any problems whatsoever. So kind of a danger of systems administration is jumping the gun and saying, oh, I've identified the problem, I'm going to go fix it. And you run down this rabbit hole, you spend 40 minutes, 45 minutes, whatever, telling the boss, I got this, I got this, I got this, no problem, it'll be back up in half an hour. And then you get to your end of your half an hour, 45 minutes, and you have fixed something, but it wasn't the something that was wrong. It is usually always worth taking an extra couple minutes just to prove that what you think is the problem is the problem. Now in certain cases, the machine is swapping to death. It's pretty obvious, right? Then you have to decide why is it swapping and how do I fix that? But in a case like this, it has a lot of open files. It's probably at the limit. It's probably the problem, but let's prove it. So how do files get opened? The software calls the open. This is what's called a system call. Software doesn't actually have the ability to access the file system. The software, any program you write, has to talk to the kernel and say, hey kernel, I would like to do this thing involving a device. This is actually really nice because as a software engineer, you don't want to deal with the vagaries of file systems and inodes and all that sort of stuff. You just want to sort of hands off say, hey kernel, I would like to open this file. I would like to read from it or write to it. Please do that for me. Oh, so we're talking about system calls. The kernel provides these services, IO goes to the kernel. There's other ones you've probably heard of, fork, change directory, exec if you want to run another program. Time, actually get the current time is a system call because your program doesn't have a clock in it. The kernel has the clock because it talks to the hardware. And the kernel uses, or NTP can keep the clock in sync. So you have to talk to the kernel if you say, what time is it? Then you could try to keep a timer, but it's not very easy to do, actually. Time is really hard. But to talk to the kernel, you have to do a small context switch. If you remember earlier, we were talking about user CPU usage, system CPU usage, idle, and IO wait. If I say I want to open this file, my program is running, it's executing, open, it calls the kernel. You've used a little bit of user CPU time. You call the kernel, you have to context switch into the kernel. It's very lightweight. It's not like switching to another program. A kernel call is pretty easy, but it's still, you are now in system time. The kernel takes over. It does whatever work it needs to do to serve your request, and then it switches back to your application. So this is what leads to system CPU usage. If you see system is really high, it's doing a lot of kernel calls. Or the kernel itself is doing a lot of work. It's kind of hard to tell. So let's talk about how we can prove that our program that we were looking at a minute ago is actually running out of, is hitting the limit on files, and that it's causing a problem. Question?
With the limits, it says there's a soft limit and a hard limit. So what's the difference?
Yes, the question was, with limits it says there's a soft limit and a hard limit, and what is the difference? I honestly don't know what the behavior is on modern kernels. I generally set them the same, but the idea, as I understand it, is that a soft limit is sort of a advisory limit. Like it can go up to that point, and the kernel may cut you off there, but you might be able to go up to the hard limit. So depending on system utilization, that's not a very detailed answer, and I apologize.
Can I just say that the soft limit is enforced, but the user is able to modify it to the hard limit?
Got it. So the update from this gentleman here is that the soft limit is enforced, but the user can self-modify their current limit up to the hard limit. So a hard limit is what the kernel says you can go no higher than this, and a soft limit is what your limit is currently. But you can use the ulimit command to update your limit up to the hard limit, if you wish. I assume that's why I set them the same then, because I wouldn't,
Why would you want to?
yeah,
If you're going,
yeah, not much benefit for me to do that. So thank you. So if we want to prove that our software is actually having a problem here, how do we do that? How do we know what our software is actually doing right now? Well, it's running, and unless you've put in log lines that say, I'm trying to open a file, I failed, you have to do something else. So we're going to talk about strace. strace is a wonderful, sort of ubiquitous tool that some people love, some people hate. There are a lot of alternatives to strace out there. If you want to get into dtrace or LTTNG, or I think perf can do system call stuff, or system tap, et cetera, et cetera, et cetera. strace is installed by default on most machines, so we'll talk about that here. So let's look at this 4 files script again. You should still have the PID, or you can ps grep for 4 files to get the PID. We're going to run strace on it. So go ahead and run this command, sudo strace-ppid. And you should see some scrolling every second or so. There'll be 4 or 5 lines that scroll by. Everybody seen this? All right.
Having a problem here.
Uh-oh. Oh, it didn't occur to me that it may not like having multiple people stracing at the same time. That's damn it. It's fine.
Yeah, you know,
I can demo it on the screen.
that was one thing we didn't check last night.
Yeah, I ran it through with one person, but
Yeah.
okay. So let me drag this over here. If you were able to get into strace, this is too small. Ah, God. Can you change the font size in this thing? It's not the menu. Terminal.
View. So I hit view, there was a zoom button.
Oh, yeah. Zoom in. 12 plus. Bigger? Okay. So this is strace running, and you can see something is happening every second. strace shows you the system calls that your process is making, and it tells you what the kernel is giving back to your process. So it's sort of it traces the process from the time that it executes a system call, so from the time your process hands control to the kernel to the time that the kernel returns. And you can see exactly what has happened. So in this case, it's calling open. It passes a parameter, /tmp/a file name, some arguments, which we're not going to worry about here, but these are when you call open, you can say, I want to write to this file, I want to read from this file, I want to truncate it, etc. I want to append to it. And then the kernel returns and gives you an answer. Well, in this case, it's pretty clearly it's returning EM file, and if you run man open, and if you have the right documentation packages installed, you will see that the open system call can return EM file, which means too many open files. You are unable to open further files. I would say that that conclusively proves that our program is having a problem opening files.
Trying an awful long time, too.
Yeah, it keeps going,
11:41.
and then it sleeps for a second, because otherwise it would spam. All right, where'd my presentation go? Okay, so clearly it's broken. It's trying to open files, it can't. We've seen that the ulimit was 1024. The program is trying to open more files than that. The kernel is saying, sorry, you can't do that. There are fixes to this. You can open fewer files, which is pretty much the main fix if you're the user, if you're not root. But if we're talking about you're the sysadmin, you can raise the limits on the system. I'm not going to go into the specifics of that because that involves editing config files and limits.conf, and it depends on your distribution and which PAM modules you have installed. But one of the best tools as a systems administrator is, man, I got this problem. I'm going to go look on Google for that, or I'm going to go look on Bing or whatever your search engine of choice is. I use Google. I've had good experiences with it. Search for the problem you're having. Linux, Ubuntu, or Debian, Red Hat, whatever your distribution is, raise ulimit. You will get a lot of people saying, oh, I ran out of limits, or I'm getting EM file. How do I fix that? And somebody will respond and say, here's the file you edit. Here's what you do. You probably have to restart your process, or you certainly have to restart it. You may have to restart your user account, because PAM usually sets limits when you log in. But it's pretty straightforward. So moving a little bit on from files, it's all turtles. Linux really likes the file system concept. Sockets are files. Unix datagram pipes are files. All of these things fit within sort of the file ideology or idea. You have a thing, you want to read from it, you want to write to it. It is connected to something. Linux has abstracted the idea of where it's connected to from the whole process of pretty much opening it and talking about it. File descriptors work for all of those. So it's the same number space. You can have in this case, you can have 1,024 open, whatever, sockets, pipes, files, etc. So you may think, oh, I'm not going to write software that opens a lot of sockets or opens a lot of files. But if you're writing a server, a web server, a proxy server, something like that, it's going to receive a lot of connections. You're going to accept a lot of users, probably, if it's popular. You're going to run into ulimits. For whatever reason, ulimits are one of the darn things that always bite every sysadmin like roughly every 6 months. We just had another thing at work the other day where we were unable to accept more connections, and it was kind of, weren't really sure what was going on until we go, oh, we hit our 30,000 U limit again, so let's raise it to 40,000. And in 6 months, we're going to hit 40,000, and we're going to have to raise it to 50,000. And then once you start going beyond that, you start wondering about getting another machine, because I think there's a hard cap of 65K or 64K, so, which is a kernel limit. Recompile the kernel. If the answer to a question is recompile the kernel, be a little afraid.
Wrong question.
Yeah, wrong question.
Now we're definitely outside the scope of this talk.
Yes. I mean, it's a great solution to many problems, and certainly if you're in certain environments, you do have to compile the kernel for things, but generally it is saner to go with an established distribution, right? Red Hat, Fedora Core, whatever, Scientific Linux, CentOS, Ubuntu, Debian. I don't really care which one you choose. They all have pros and cons. But it's generally safer to go with one of the established ones. It's easier to find information if you're looking online, because if you say, oh, I've got a custom kernel, a lot of people are going to say, it's probably your custom kernel, because it probably is. The kernels that are built and shipped by distributions usually work pretty well. But again, every sysadmin will have their own opinion. I've worked with places where they really compiled their own kernels, and they had to. At Mozilla, we did compile our own kernels, because there were certain, when you're dealing with 100 million users, and we're funneling, we didn't have a lot of hardware. We had a decent amount, but we needed to tune a couple of things that were compile time parameters. All right, so we're going to talk about another program now. We get started here. Oop. All right, so I'm running another program. It's called 5-Network. We're going to do the same dance. You suspect that there's something going on with this, or you want to understand what this program is doing. So you run PS, you get the PID. Now we're going to go back to LSOF again. LSOF NP PID. It should only be like 5 lines this time, 4 or 5. As a point of interest, if you're a developer, you're familiar with standard in, standard out, and standard error. Those are usually opened as file descriptors, and they will be the first 3 that you see, like 0, 1, and 2. You should see the bottom line in this particular case says TCP, right? This is, and it'll say TCP colon 7000, I think it is. This software has an open TCP connection. It shows up in the list of files because as far as Linux is concerned, it's a file. It has a file descriptor, and if you as a program want to interact with this socket, you use the file descriptor. So A lot of the time, if you're debugging networking-related problems, you use a lot of the same tools as if you're debugging file-related problems. LSOF, strace, etc. So let's test this. This is a server. It is doing something. It serves requests. Actually, I mean, you can try this from your local machine with the IP, or you can telnet localhost 7000, which was easier, and I should have thought of that. Since you're on the machine, go ahead and telnet localhost 7000. And it may take a little while because there's so many of you, but eventually you should see the time is something, and it'll say disconnecting now, or thanks for playing, or something like that. I forget.
Thank you for visiting.
Thank you for visiting. It's a well-behaved little script. Well, I'm saying strace because, but we can't do that, but that's okay, because if you were to strace it, you would see this to begin with. If nobody was connecting to this service and you just said strace this script, you would see this. This is strace's way of saying that you have called the kernel, but the kernel hasn't finished yet. It has not returned. So your program is paused while this system call is running. Except if you're a C programmer or a Perl programmer, you've used except, it says, I've got a network connection, a socket. I'm listening on that socket. I would like to wait for somebody to connect to me. 3, in this case, is the file descriptor. Your listening socket is file descriptor 3. So you're saying, I'm calling except on 3, and you're waiting. Eventually, when somebody connects, as you all just did, this will happen. It will finish, and these are the return parameters. It returns, technically you have passed a struct that the kernel has then filled out when it gets back to you, but it fills it out with this data. You have an internet connection on port 39474 on this address. That is the remote host. And by the way, the file descriptor of your remote host is 4. So now you have a new file descriptor 4 that is connected to this person, whoever that may be. And strace will tell you that. Then you see a bunch of this. I've graded out because it's not relevant here. I believe this is Perl specific. It is saying the IO module has gotten this FD and it's trying to set it up to get it into a known good state with ioctls, which are IO controls. These don't work. They return -1s and -1s and -1s because the kernel is like, this isn't a file. This is a socket. It doesn't hurt anything. It just wastes a few cycles trying to set up the socket, or trying to set up what would have been the file. Then you see this system call, stat. Stat is a system call that says, tell me something about this file, or I want to know something about this file. And the file that it wants to know about is etc local time. You know that what this program does, because you've used it, it tells you what time it is. And then it says, thanks for visiting. So it's kind of easy to assume that this is how it figures out what time it is. We talked a bit about programs don't actually have the time inside. They have to talk to the kernel. There's a couple of ways of getting the current time. This is one of them, and this is the way that calling local time in Perl 514 gets the time. So then the system call write, as you expect. You're saying, I want to write to file descriptor number 4. Here's some text. I want to write, the time is February 6th, 1:34:22. And then the kernel returns, or you're saying I'm writing 38 bytes. The kernel returns and says, all right, you wrote 38 bytes. From your program's perspective, that's all you have to do to write to a socket. From the kernel's perspective, a lot of stuff has just happened related to sending this down to the network card through the device drivers and actually, well, it may or may not be sending a packet yet, depending on a lot of things that we're not really going to go into the depths of TCP here. But in essence, your program has said, I want to send this data. And the kernel said, got it. And so if you were tracing this, you would know that that's just happened. Some more things happen. These are processor mask stuff. I don't actually know exactly what Perl is trying to achieve by doing this. But what? But it works. Yeah, stuff happens, it makes it happy. But so when you're S-tracing stuff, you see a lot of, especially if you're in a interpreted language, if you're running Python, if you're running Perl, Ruby, etc., the system is, the interpreter is doing a lot of work behind the scenes to manage your program state, stuff that if you were writing a C program, you would normally have to think about or worry about. But in this case, you don't, because here Perl is handling it for me. Some of it is necessary, some of it is not. Some of it I can tell you what it does, some of it I can't. Then this program executes an nanosleep, just so that we have a little bit of delay here.
Power nap, right?
It's like a power nap, yes. Much like programs can't know what time it is, they can't stop running. They can busy loop, or they can tell the kernel, hey, you know, I want to take a break for a bit. Can I sleep? Can you just like wake me up in a second? And so when you call nanosleep, or in Perl you just say sleep 1 here, the kernel says, all right, it deschedules your process, lets a second go by, and then the system call returns. Pretty straightforward. If you were in the talk yesterday about making things go faster by Anton, he talked about sched yield, which is another way of saying, you know, I kind of want to give control back to the scheduler to allow other stuff to happen, but he says don't do that. So if you're writing software, don't do that. But you might see that, in fact, at work we have a lot of problems with Haskell. It gets into sched yield loops where all the threads are starting, they're all yielding at the same time, and then nothing gets done. It's very unhappy. The next thing after the sleep comes back, it writes, thank you for visiting. So this software has accepted your connection, got the current time, told you the time, slept for a second, and then said thanks for visiting. And then it closes your socket. And when you were telnetting to the service, you probably saw this. It would say connection closed by remote host, I believe is the specific. So this is a pretty straightforward strace. If you start tracing things like MySQL or Apache or multi-threaded processes, this gets very, very busy very, very fast. And there are a lot of commands you can use to strace to say, you know, look, I only care about network calls. I only care about open calls. I only care about whatever it is. I really encourage to read the man page for strace and play around with it, right? It generally doesn't hurt things to strace a running program. It can interrupt certain syscalls, like if you're doing networking programs, ePOL, etc., will get interrupted, but then they resume, and it's fine. It does put load on the system, though, so you shouldn't just keep running strace on your main database all the time. Generally not safe. So what we just saw there also is that tracing shows you data, too. And this is, in my opinion, a really, really helpful debugging system. If you are trying to figure out what's going on with your server, you can see how the data is moving around. This is, for example, really helpful if you're running a website and you have your web server running and it's being really slow. Somebody says, man, this is really slow. And you want to know what exactly is being slow, right? You can run top and you can say, oh, it's not using a lot of CPU. It's using, 10%. So clearly my web server is not running at capacity. Well, what can I do? Well, I can strace it. And with strace, you will see we don't have any read calls there, but you could, for example, say read, 17, and then it sits there for 30 seconds or whatever, and then it completes, or then it goes. And you know that it sat there for some number of seconds in a read call on file descriptor 17. Then you can use LSOF to say, what is file descriptor 17? What is it trying to read from that is taking, 5 seconds? Then you look that up and it says, oh, it's connected to IP address blah, 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 port 3306. And you go, oh, it's MySQL. Because you know that MySQL is on port 3306. And then you can go look at your database. You have now used the web server to finger the database to then go say, my database is slow, what's the problem? And debugging MySQL is a whole separate talk. Separate set of talks. If you go that way though, I recommend Percona. They have a lot of good software and a lot of good, like the Percona package is really good. They have really good monitoring tools, etc. So they don't pay me, that's just a plug. Let's talk a bit about kernel. the kernel is the operating system. You're all familiar with that. It's sort of the invisible glue. The kernel basically abstracts the hardware to a point where you can write software that repeatedly runs on all sorts of hardwares. It makes your life as a programmer a lot easier. It also provides, to a sysadmin, a lot of tools for understanding what is going on and fixing things. Kernel problems. The kernel usually doesn't have a problem. Let's be honest here. Linux, as far as an operating system goes, is really stable. It is a really well done piece of software and rarely has issues of its own. Usually the problems you run into are because you've hit a limit of some sort. We talked a bit about ulimits earlier. That's one sort of limit in the kernel, but there are other limits that are deeper in the kernel that you won't run into until things are on fire. There's caches. There's network-related, bucket lists for connection tracking. There's limits to all sorts of things. One thing to be really suspicious of is powers of 2. If you ever see messages that say, or if you ever see like a status display that says, there are 65,535 files open, you probably have some sort of limit. Or if you see, there's 1,024x, right? It's really suspicious if it's exactly a power of 2 or really, really close. These are sort of intuitions that you eventually get when you've been doing a lot of stuff. So we're going to try something here. dmessage. Dmessage is it shows you the kernel's message buffer. The message buffer is sort of the things that the kernel has felt or that various kernel modules or device drivers have felt are important to record. And they get recorded in a message file or in a message buffer, which you can access with dmessage. You can also access it in varlog, and we'll talk about that in a bit. But for now, if you run this, lots of data goes screaming by.
I don't know, run don't need to run it sudo.
Oh, you don't?
No.
All right. Pro tip, you don't need sudo to run it, so yes. So run dmessage. The message log shows many things. Many things show up here. This is sort of in my test, like if I'm seeing if there's a problem with a machine, I check top, I check free, I check df, I check dmessage, because even though it's going to be once every 6 months that something shows up here, when it does, if you don't have a habit of checking it, you will spend the next 5 hours going, what is going on here? Suspicious. You might see something like out of memory, kill process or sacrifice child. Linux gets very excited about its error messages. Yes, when the memory script was running, it was getting killed. Actually, other things were probably getting killed too. I don't know. You might have lost your... No? Just the one. All right. It actually, in that case, it gives you a lot of debugging information. It tells you what the state of the system was, so you can kind of go back and see what was going on. This is, you might see the NF contract one if you're running proxies or popular websites, which is always kind of a pain. But this is, like, resolving it is pretty simple, right? You raise the contract limit. You say, you know what, kernel, allocate more memory. And assuming you have the memory to spare, it's pretty easy to fix. Assuming that the problem is just that you hit this limit and not that you're getting DOSed or your site is under attack, right? In that sort of situation, you raise it, you hit the new limit. You raise it, you hit the new limit. And then you know something is wrong.
And then you lie down and cry.
Yeah. And quit your, no. Sometimes you get really, really cryptic messages, and you just have to go, well, exception is bad. Frozen is also probably bad, because ATA is disk related, or it's, so if my disk system is throwing the exception and it's frozen, I don't know what the hell the rest of this means, but it's probably angry. Yeah. Past time to back up. Yeah. Pro tip, if you start getting errors like these and you're like, oh, I need to do a new backup, don't overwrite your last backup. Make a separate backup. Because otherwise you might go, I've got lots of blocks of zeros. Weird.
That's really neat. It compresses really well.
Oh yeah, it does compress really well. Amazon loves it and will charge you for the same amount of bytes. So the message log will show up lots of things that are really just kind of random and don't happen very often, but the kernel notices, right? If your network card is going bad, you might start seeing messages in here about, it's stalling, commands are failing, or something like that. If your disk is going bad, you start to see stuff like this. And it may not be like it is dead right now, but it may be the kernel says, I tried to send this command and it took 35 milliseconds. That's really strange. So it's good to just sort of pay attention. We talked a bit about understanding your environment. Knowing what is normal in your kernel message log is a very important part of that. More places to look. Varlog. Varlog is sort of the dumping ground of every bit of software on your machine that says, I've got something to say. And it will fill this directory prodigiously with lots of data. Apache will be writing here, MySQL will be writing here, maybe if you're lucky. Lots of things will write here. You'll probably want to... What?
You've been working with Java, right?
Yeah, seriously.
Anything that's not installed by DKG or Yum, it's probably somewhere else.
Oh, yeah. Yeah, there's other places you can check, but varlog is a good place. I mean, syslog goes here, and a lot of things use syslog. There's a lot of stuff here in sort of my, I have a problem right now, sort by the recently updated time, because if there's a problem, it's probably writing to log files, and you can eliminate 90% of the log files by saying, I don't care about things that last got updated 6 hours ago. I just want to see things that are updated 2 minutes ago, 1 minute ago. So you can sort of work backwards from there. And ls has flags for sort by time. T is the main one here, R is reverse, so it shows up at the top. Loud logs are often unhappy. Hardware failure usually shows up in one of those. I mean, if your machine hasn't actually gone down, you usually see hardware failing or failed in one of these logs, usually the kernel message buffer. Also, I didn't really talk about hardware RAID, but if you do have a hardware RAID on your system, you'll often see messages here from whatever the RAID manager is, Storeman or LSI's software that says, disk is failing. And if you don't have that monitored, this is a good way to know. Feel free to, you can't actually see a lot of the logs because you don't have full root access. A lot of log reading requires root. But you can poke around in the directory if you wish and see what you can see. Other random stuff that's in here is like if you're running a machine that people connect to and users are saying, hey, I can't connect, there's an auth log that'll probably tell you, the permissions on their SSH authorized keys file are bad. Little stuff like that is just helpful. So let's kind of summarize what we've talked about here. My personal process, and if you're working on systems, you will come up with your own, is to check each of the components, see what the CPU is doing, see what the RAM is doing, see what the disks are doing, understand what it looks like, look at top, see what the software is doing. Is something running 100% CPU? Are a lot of things running a lot of CPU? Are they using a ton of memory? If your system looks fine, but people are reporting problems, it's probably software. You can trace, you can look at log files, and analyze well before you spend a lot of time fixing stuff, because some of these may not take a lot of time to fix, but there's also sort of an old adage of the number of moving parts you have increases the complexity of your problem. So you don't want to tune this, 5 different things in the kernel, and then stuff is better, but you don't know exactly what fixed it. It's better to change one thing at a time and to understand exactly what you're doing. I want to harp on this again, because to me this is sort of like the bread and butter of being a quick and efficient systems administrator. Familiarity. If you just do it as an afterthought, your life will be painful and hard. It is like any other thing, right? The more you do it, the more you play with the machines, the more you look at them, the better you will understand them, the better you will be able to diagnose them when there's a problem. This is, you wouldn't want to go to the doctor who just every 6 months says, I need another paycheck, I'm going to show up at the hospital and do some surgery, right? You want the person who's there every day taking care of business. Same thing with systems administration. It is a skill, it requires practice, and in each environment. I usually keep a shell open and I just run top. You can keep it running, take a look at it, look at dmessage, whatever. Pretty easy to do. Next steps, if you're interested in learning more and going further with this, we have talked a lot about here's how you can diagnose things right now on the fly. It is really inefficient to spend your day running top and staring at it. It's not a good use of your time. I mean, you should understand your environment, but there are a host of tools. I've just got a kind of a grab bag here of things that make your life easier. Nagios is kind of the old tried and true thing that people talk about a lot. There are other ones out there, Zendesk. There's other ones. I use Nagios. I'm most familiar with it. It has a lot of warts, but it works. But you can configure things in there and say, hey, let me know when the disk gets 90% full, or let me know when the CPU is over 90%, or let me know when... Yeah. Let me know when this is broken. Let me know when my software is down. Let me know when the service is unavailable. Let me know when DNS stops resolving. Stuff like that. One of the best tips for making an effective uptime environment is whenever you have a problem, build an alert for it. I mean, there's a little discretion here, but when we run into the NF contract and the kernel message log, I now have an alert that every 5 minutes checks varlog syslog or varlog messages and looks for those messages. And if one of them happens, I get paged within minutes. I don't have to sit there and watch the kernel log. You will get bit by a lot of things, but the more you cover them with automated tools, the less you get bit in the future. That's monitoring, which is sort of is it working right now? There's also trending. I'm actually not sure if there's a good word for this, but it's sort of I want to graph my CPU usage over time. And I want to be able to go look at a graph and say, for the last 6 months, how have my servers been doing? This is really, really helpful because you, as a sysadmin, will spend time on your machines and you will get to understand how it feels. But if over 6 months it has gotten busier and busier, bit by bit, you probably won't notice that. You'll just go, it's a little slower than last week, but no problem. But if you look at the graph, you go, oh, it's gone up, right, or up to the right. Now we're hitting 90% peaks every day. I should probably figure out what to do about that. So there's a lot of tools for that. Ganglia is a pretty easy one. You just run it, and it gives you a bunch of graphs. Cacti requires a little more configuration, but it's very pretty, and it works pretty well. Those are RRD based. If you're familiar with RRD, great. If you're not, it is a low storage space, low fidelity storage system, which works pretty well. Some people like it, some people hate it. OpenTSDB is a time series database that is high fidelity. You could go back a year and a half and say, show me exactly what was happening at 4 p.m. on Tuesday afternoon, and you won't lose any data. It's pretty nice, although it requires a lot of setup. If you start building a large environment, you've got 2 machines, you can SSH to them, no problem. You got 5 machines, you can still SSH to them and run your apt-get updates one by one. That's okay. You start getting 10, you start getting really annoyed whenever people want to deploy software. You start getting 30 machines, and by then you should be using Fabric or, it's not Quilt, it's something like that. That allows you to, mCollective I think is the other one. Capistrano, yep. There's a lot of software that does this. Find one that you like. Parallel SSH is another really kind of tried and true one. But you can say, hey, in this case, you can say, hey, Fabric, I want to run on the app nodes, and you have separately configured it and said the app nodes are machines X through Z. And it'll connect to each of them and run your command, so you only have to run it once, and then it does everything, it does each step for you. Saves you a lot of time. Puppet and Chef, I cannot emphasize enough, if you're going to manage more than like 1 or 2 machines, configuration management, right? Having repeatable, reproducible software that basically, for those of you who don't know, configuration management is the art of setting up a set of rules that say, these machines should have this software installed, these configuration files, this thing should be running, this thing should not be running, and you don't have to worry about it. You can set up Puppet and Chef to run every 30 minutes or whatever, and they will just like, if somebody connects to one of your machines and reconfigures something or uninstalls Apache on accident, Puppet will come in and, if you have it configured, reinstall it for you, get it started back up. This saves you a lot of time as your infrastructure gets larger and you have to worry about, you will never notice, right? If you have 15 app servers, you may not notice that one of them is misconfigured. And your users will start sending in reports saying,
115 times.
1 in 15 times, the website doesn't work. And you will pull your hair out trying to figure out what is going on here. Yes, absolutely. There is a dark side to these, right? If you have Puppet running every 30 minutes and you put in a thing that your Puppet rules or your recipes, or chef recipes, Puppet rules, whatever, are misconfigured and uninstall Apache, for example, the next 30 minutes will be very interesting as you start getting paged because app 7 is down, app 10 is down, app 4 is down, and you're like, why are my app servers dying every couple minutes?
I was thinking the other way around. If you had an issue with one server, you've gone in there and sorted out, put a temporary workaround for the problem, and then Chef comes in and apologizes.
Yes. The point was made by the audience for the recording that the opposite of that is also true with Puppet, that if you have a problem on app 7 and you connect to app 7 and you go, oh, I see what the problem is, and you fix it, and then you go to lunch or something else, Puppet comes in and goes, weird, somebody made a change here, and wipes it out. And then you have to redo all your work, and then you remember to do it in Puppet this time. So you eventually learn habits to shut it off on that machine while you wait for it. But then, if you're like me, you have Nagios making sure Puppet is running. So then you've shut it off, and then Nagios pages and said, hey, somebody shut off Puppet. And it's like, ah. So eventually, if you really get into systems administration, sometimes you fight the machines, and sometimes they win. So that's what I have prepared. I have 10 minutes left or so, and I would love to open the floor for questions, comments, anything people want to say. There's one in the back. Microphone will come to you. We appreciate that because the people who will watch this later will want to hear.
Hey, going. I was wondering if you know of any trending tools for Nagios analytics.
Yes, there are plugins for Nagios that allow you to get trending out of it. I forget the name of it. It's not live status.
PNB.
Is what?
PNB for Nagios.
PNB? Yes. So if you look up on Google, there are tools for that. They plug in Nagios. Nagios actually keeps track of how long tests are taking to run and a lot of other performance data.
It's the history that
Right. Yep. I personally haven't. Something was beeping. I personally don't use them, but they work. There's many ways to skin the cat.
Can Nagios not figure out and report things like this process is using all of its file limits? Like that seems kind of straightforward. I don't know.
So for Nagios, you can check anything you can write a shell script to check, basically. Because how it works is it looks at the exit code of your shell script. So you can. You just have to decide how you want to check it and then write a little script for it. It comes with a lot of plugins for like HTTP checks, SSL checks, DNS resolutions, memory, disk, etc. I don't know if file descriptors for a process is one of them, but you could certainly write one.
There's a nice little plugin called CheckMK for Nagios, and it does a lot of this sort of stuff out of the box, like CPU, disk usage, all that sort of thing, and automatically sets it up so you don't have to set anything.
Yes, there are a lot of, Nagios has been around since the mid-90s, I believe it is, late 90s, and a lot of people have written software for it. So, you might think, it's going to take me 2 minutes to write a plugin. That's true, but if you look online, there's really good plugins for like MySQL, for Redis, for MongoDB, for whatever you might want to have. There are really good plugins out there, and I highly recommend using them as opposed to just rolling your own immediately. And then contribute back, right? That's one of the things that's really nice.
One of the things that's really good with CheckMK, you actually have a local script that you can put, so you can run your own local tests, and every time it connects, it runs all its checks, as well as anything in the locals checks, and it automatically has to plug in down to complete analysis with the additional checks, and you can log in.
Nice. It was pointed out by the audience that CheckMK can also run local checks, so you can add your own to it as opposed to just depending on what it has in there, which is really helpful. Thank you.
Hi. Playing with Nagios a little bit, and I've used it a lot for like sort of direct service checks. So go and check a web service, see it's up. I'm sort of in the 5-minute polling type sort of setup with 2 or 3 retries.
Right.
I've got a really sort of interesting bunch of users that will notice things in less than that time. Do you ever
Yes.
sort of wind things back? And if so, because there seems to be some gotchas in the Nagios documentation about don't set your check frequency below 1 minute or
Yes.
evil demons will come and eat you.
He has occasionally in the past called me human Nagios.
Yeah.
I will page him before Nagios does.
So the risk you run, and we get into sort of like monitoring theories, the closer you make your checks and the more sensitive, the more false positives. Exactly. So I wouldn't dial it down below a minute with like 2 retries, maybe 3. That gives you a 2 to 3 minute window. If you really want faster, what I've done in the past is I use an alerting service called PagerDuty, which is the thing that can call your phone and then send you an SMS and send you an email when something is wrong. And I've written a separate script that basically just loops, and every 3 seconds it checks the service. And if it's a problem, then it talks to PagerDuty and it bypasses Nagios. So it keeps the sort of the slower monitoring away from the really, really need this right now. But I usually end up turning that off because the false positives. Right? At 3 a.m. when your service provider does a little bit of network maintenance and you have 10 seconds of packet loss, I don't want to wake up. I really don't. Nobody cares. Any other questions?
I think you covered absolutely everything, apparently. There you go. We're leaving this session knowing everything about systems administration.
I wish.
Okay, everyone, please give a thank you to Mark Smith. And we have a little goodie here from Linux Conference Australia 2013. There you go.
Nice.
Okay. Thank you.
Thank you all for coming.